So welcome to the afternoon session of the 19th meeting. So today we're very happy to have as our first speaker in the afternoon, Lukas from Oxford, and he's going to tell us about reinforcement, what a complicated word, reinforcement learning and string model building. Please take it.
Okay. Yeah, thanks very much. Can you hear me?
Yeah.
Okay, right. Thanks very much. And thanks very much to the organizers, of course. So yeah, this is about reinforcement learning and string model building. And this is based on work with Andre Constantin and my student Thomas Harway. And then for a last part, which actually has to do with genetic algorithms, it's also with Steve Abel. And maybe I should say upfront, while the title looks a little bit specialized, this is actually about, there's a general context here, which is about trying to use machine learning to learn about certain mathematical structures with prescribed properties. So the general principle here might have applications in lots of areas of physics and in mathematics. Okay, so here's the outline. So a bit of introduction and motivation, and then a very short introduction into reinforcement learning. And then I'll demonstrate reinforcement learning in the context of a toy example, which is to search for line bundles with certain prescribed properties on a given Calabi-Yau manifold. And then comes the actual application, which is to a certain class of string models for which we would like to identify models with certain nice properties, physically nice properties. And I'll show how RL can be used to do that. And then if I have time, I'll get to what is perhaps a competing or alternative way of approaching the same problem, which is genetic algorithms. Okay, so introduction. So as probably most of you know, string theory, among many other things, also generates very large sets of diverse types of data, which might be Calabi-Yau data, bundle data, all sorts of things. And because it does that, there are a number of challenges that come with this feature of string theory. And I've listed some of these challenges here. So one of them is that some of this data might actually be rather difficult to compute and might be very slow to compute. And an example of that is cohomology calculations carried out in the typical way, traditional way, with commutative algebra. The second challenge might be that the data sets are very large. For example, the data sets of Calabi-Yau manifolds coming from the Kreutzer-Skarke list. And then thirdly, we might be missing structural insight. We can sort of do model by model, but sometimes it's difficult to see the bigger picture, which might make things like bottom-up model building quite difficult. So an obvious question that people have started to look at a few years ago is, can machine learning help in this context? And broadly speaking, I think the answer to that is yes. And machine learning in the context of supervised machine learning has been tried out on quite a few pieces of string data. I've listed a few examples down here, some of which actually we've had talks about in this meeting. And it is, in some sense, quite remarkable that that machine learning methods work on such a diverse set of data. Now, what I would argue is that supervised machine learning may help with the first point here. So once you've trained your network, it might help computing similar but unseen data more quickly than you would have done with conventional methods. And it might sort of incrementally help with the second point, but the structural insight is often difficult because machine learning works a bit like a black box. So in this talk, rather than talking about supervised machine learning, I would like to talk about reinforcement learning. And perhaps it's fair to say that there is a chance that that might help with point 2 and 3. So I will sort of explain how it might help exploring really large data sets and how it might help gaining some structural insight. So it is of course known from various applications, starting perhaps with the Google AlphaGo Zero application, but also various papers applying it to string theory, that RL can be very efficient in exploring large environments, and we'll see why that is. And unlike supervised learning, reinforcement learning is in some sense constructive, and we'll see what that means precisely. So the more specific question here is, can reinforcement learning be used for string theory and possibly also for particle physics model building? And then more specifically, the sub-questions are, can we explore large classes of string models? Can we, within those classes, identify models with certain prescribed properties, for example, models with nice physical properties? And perhaps more ambitiously, can we then identify or extract model building strategies from these RL systems? And I'll be studying these questions in a certain specific string context, which are heterotic flux, vacua, and Calabi-Yau, so geometrical compactifications. But as I said earlier, the general principle, I think, probably does apply to a much wider class of structures in physics and mathematics. So let me say a few things about reinforcement learning. That's basically just a cartoon. So there are sort of lots of components to reinforcement learning. So let me just go through these various components. So one of them is the environment of reinforcement learning. So the environment can be all sorts of things. It consists of a number of states. You have just drawn these geometrical figures, but there can be physical theories or string compactifications. And you want to explore this environment, and this is done by an agent. So the agent walks around, goes from state to state, and thereby sweeps out what is called an episode. And there is a goal in doing that. The goal might be, for example, in the simple environment, to find geometrical objects with lots of faces, let's say. And so as the agent walks along from state to state, they will pick up a reward or a penalty depending on whether they go to a better or worse state. So for example, as the agent goes from here to here, there's a penalty, and as they go from here to here and to that state, there'll be a reward. And then if the agent arrives at a really perfect state like this one here, which is called a terminal state, then they might get an extra bonus for that. Now, those episodes that the agent performs, they are not unguided. They are in fact guided in the simplest way, say by a policy network. So that's a neural network which, as an input, receives a state. So one of those states here in the environment, and then as an output produces an action. So tells the agent, in other words, where to go next. And so these two elements of RL, they are now coupled. So one coupling is that as the agent performs one of these episodes, it produces a batch of data, a batch of triplets, which consists of state, action, and reward picked up after each step. And this batch of data is then used to train the neural network, to improve the neural network in some sense, so that the policy becomes more efficient, guiding to good or terminal states. And then with that updated neural network, a new episode is performed, hopefully with an even more optimized outcome. And then the cycle repeats unless there is some degree of convergence until the policy network settles on a particular policy. So that's the basic structure, at least in the simplest case. So how would you apply this to model building? So what we want in this case is to explore large classes of string models and find identify those with certain prescribed properties. And here we'll take these properties to be basically having a good phenomenological spectrum, so like a spectrum like the standard model. So the mathematical context here is the Markov decision process, so that is being identified with a certain physics context, in the sense that the environment now becomes a family of string models, or possibly also quantum field theory models. The state, where each state corresponds to a specific model within this class, an action, so going from state to state, will typically amount to a small modification of a model, and I will be more precise what that means in the examples. And then the reward will, in some sense, measure to what extent you improve or make worse the desired properties as you go from one state to the next. So there are two examples that we have been looking at. One has to do with quantum field theory model building, which is to do with Fogart-Nielsen models for quark masses. So that's in this paper here with Thomas Harvey. And I'm not going to talk about this, but if you're interested, you can have a look at this paper. But in this talk, I'll be focusing on these kinds of adrotic Calabi-Yau models with monad bundles. And I'll explain what they are, of course. So these will be explored with RL. Now, RL comes in a number of flavors. Actually, what I've shown on the previous slide was the sort of the simplest version of reinforcement learning, which goes under the name of reinforce, but there are other slightly more sophisticated methods. One of them is the actor-critic one. So we'll have implementations of either of these. They're realized as Mathematica packages, and we'll do most of our exploration using either one of these methods. Okay, so that was the introduction. So now let me get to illustrating that with a particular very simple toy example. So what's the mathematics? So we're looking at a particular fixed Calabi-Yau manifold, Calabi-Yau threefold X, and on this Calabi-Yau threefold, we want to consider all the line bundles, and those line bundles, they'll be in practice parameterized by some integer vector k with as many entries as the Picard number of the Calabi-Yau. And the question that we want to ask is, can we find among those line bundles those for which the index, which is computed by this formula here, for which this index has a particular given value. So that's what I say here. So we'd like to find line bundles with given target index. So then again, the match between the various ingredients of the reinforcement learning system with the mathematical system. So the environment in this case consists of all line bundles, but represented by integer vectors of a certain dimension. And for practical reasons, to make it finite, you have the entries within a certain range. So each state is one of these integer vectors. An action in this context will just be taking one of these integer vectors and adding or subtracting one from one of its components while leaving the others unchanged. Then there's a certain factor here which has to do with calculating the return from the reward, which is set to a value pretty close to 1. And then the reward itself is being computed in terms of a value that we assign to each of these states, which just measures the deviation of the index of the state from the given target index. And then the actual reward will be computed from this value, rather from the change of this value as you go from one state to the next. Okay, so we have to do this for a particular example. So we do it for a very, very simple Calabi-Yau manifold, which is called the bicubic, given as this bicubic hypersurface in P2 times P2. So this has Picard number 2, meaning that the line bundles on this space they are represented by 2 integers, so it's a 2-dimensional system. And for the target index, we take just 18. So here is what happens during training. So this graph here is the loss during training. So you see that that approaches 0 very quickly, as it should. But perhaps more impressively, this graph here shows the number of terminal episodes. So that is the number of episodes that end with a line bundle with the correct target index 18. And that goes from 0 very quickly up to 1. So after a short period, so this only takes a few minutes of training on a single CPU. After a few minutes, this neural network will guide you to line bundles with the correct target index, basically with 100% of the time. And at the same time, the average length of an episode decreases down to about 5. So it guides you to that terminal state rather quickly. Oops, sorry. So just to summarize this, so the train policy network in this case has sort of 100% efficiency in guiding you to terminal states. It does so in a very small number of steps. And not surprisingly, because the environment is so small, it's already found all terminal states during training. So the nice thing about this environment is that it's easy to visualize. It's just 2-dimensional. So K1 and K2 here are just those 2 line bundle integers, and each point in this plot corresponds to 1 line bundle. And the thick black dots here, they correspond to the line bundles with the right target index 18. So if we take the trained network and we perform some sample trajectories, some sample episodes, then that's shown here. So this shows an episode which sort of starts from this pink point here, and then the trained network will guide it fairly efficiently to one of, well, what was the black point, so a terminal state, and the same thing happens here. So you pick a random starting point up here, and then it guides you quite efficiently to a terminal state. So you can do this a bit more systematically. So you can just, because it's such a small environment, just a couple of hundred states or something, you can just start an episode at each state in this environment, and then ask which terminal state will that initial state actually be guided to by the train network. And in this way, obtain some plot which shows the various basins of attraction for those terminal states. So what this plot means is that when you start from any initial state, say in this green region here, then the neural network will guide you from there to the corresponding terminal state, which is that empty dot here at the corner of the green region, and similar for the other regions. So that's very easy to do because it's so small, but this plot is in some sense instructive because it tells you why RL can be quite effective in exploring large environments, even though that is not a large environment, but I think it gives a nice intuition of why that's the case. And to see that, imagine you wanted to find the terminal states, the terminal states in here, by just a systematic scan through all the states. Then of course your algorithm would scan with the total number of states. But if you do this with RL, so if you have a trained RL network, then really all you need to do is pick one state, one initial state per basin of attraction, per domain here. And then for each such state, the RL system will guide you very quickly to the terminal state that it attracts to. So in other words, for RL, very roughly, this would scale like the number of terminal states, which of course in general will be much smaller. That's of course not entirely true. That's sort of roughly true. As you can see, the size of these various domains can be quite different, but I think the intuitive idea is probably clear. Okay, so that was the toy example. So before I get to the actual example, are there any questions?
Can I ask a question on that?
Sure.
So you were running the algorithm greedily, or is this an average over the terminal states they end up given the starting state?
Yeah, this is policy based. So it's from the policy network.
Yeah, and so you're always taking the best recommended action from that one in order to obtain this plot, because during training, of course, you have some.
It's probabilistic.
Okay, so in this plot, this is an average over different runs that sort of, because
sorry,
the same starting state might end up in
sorry.
two.
Okay, so sorry. The training, for the training we do it probabilistic, but this plot is actually deterministic in the sense that you take the biggest. I mean, you take the you select the action with the largest probability.
Yeah. Okay. Thank you.
Yeah.
Hi, Lucas. Hi, Andre.
Hi, Tristan.
I was wondering about a curious difference between this particular plot and the one on the previous slide.
Ah, you caught me.
This plot does not have the sort of hallmark 45-degree symmetry, which the previous plot does. So it seems like the basins of this method somehow have a different characteristic.
Yes, and there is a certain degree of in fact, if you train the system again, the plot will look qualitatively the same, but different, and it won't have the symmetry typically. So there's a degree of randomness in there that does not respect the sort of Z2 symmetry that you have for the bicubic. So this has to do with initial states are picked randomly, and the carrying out the episodes is to some degree a random process.
I was worried about that because I was worried that maybe then there is some kind of an artifact in this learning mechanism, and it might end up missing some of the goals, some of the correct solutions.
Well, in this case, it doesn't. That's what this that's what this diagram demonstrates. I mean, I imagine you could build that in. I mean, you could, for example, you could artificially, you could by hand restrict the environment to only have states where K1 is greater or equal than K2. So basically introduce an ordering.
Mm-hmm.
And in that way, you sort of remove this Z2 redundancy. But because it's random processes, I don't think that you can expect this to be Z2 symmetric if you include the whole environment.
Okay, thank you.
Mm-hmm.
I mean, if you trained it longer, and punished, so if you used the reward that punished more steps, or equivalently, if you introduce a discount factor, eventually it should always go to the closest state. So, for example, for the red one, if you look at the red line, so next to the terminal state on the red line, there's a green dot. So it would walk quite far in order to get to the green solution, rather than sort of just take a step left and go to the terminal state on the left. So I imagine if you trained it longer, you would get some Voronoi type of tessellation of this plane, where you're always sort of going to the closest.
Yeah, that could be. Yeah, I mean, maybe we haven't optimized it as far as necessary to really make it go to the nearest. As you can see from this plot, it's not always going to the nearest state. I mean, it sometimes does, but you know, if you had it optimized in that way, then I guess then it would have to come out symmetrically. Yes.
Sorry, can I just quickly add something as well? I was going to say when we were making this plot, it's worth noting, because we're treating it as Fabian was saying, this is a kind of greedy algorithm. We're just taking the highest probability. You don't really see that, for example, in the top right corner, most of the probabilities there are actually quite small. So even though it looks like, everything goes straight to green, if we're still treating it kind of probabilistically, there's actually still quite a large probability it could end up at any of those kind of four closest points. So if we look to the probabilities, you may find you kind of have some of this symmetry still kind of looks like it's there, but because we've taken greedy, one of them is just slightly higher probability there, and it's kind of messing up a bit.
Okay.
Thank you.
Is that already right? Can I move on? Okay, thanks. Okay, so what I want to talk about next is bundles, so flux over Calabi-Yau manifolds. So this the number of these things is again controlled by the Picard number, but also by the rank of the bundle. And just to see what the size of these environments is, just let's start with the abelian flux, by which I just mean sum of line bundles. So this is sort of a sum of what we had before. So R line bundles, which would then be represented by an integer matrix of size h times r. So if you have roughly 10 states per entry, then that would be about 10 to the hr states. And so for such things, scans have been performed, and that has been pushed up to about Picard number 6 for rank 5, which is about 10 to the 30 states, which sounds quite a lot, and it is quite a lot. And the only reason that was really possible is because for line bundle sums, you can check many of the properties that you're interested in line bundle by line bundle. Sorry, was there a question?
Your screen might be frozen. We still see
Okay. Yeah, it is indeed. Sorry. Let me stop sharing and do this again. See if that helps. Sorry. Okay. Can you see this?
Yes.
And it works.
Okay, so yeah, so I was talking about these line bundle sums. So the reason you can explore these very large environments is because some of the properties can be checked line bundle by line bundle. So in effect, that means that many of the 10 to the 30 states never need to be looked at. Now, on the other hand, if you're looking at bundles with non-abelian structure groups, so something that you might, for example, define by a monad sequence like that, where B and C are individually line bundle sums, that is again quite a large environment typically. But unlike for the abelian case, it's not really possible now to check the properties of V, or some properties at least, knowing just a few of those line bundles. You really need to know the entire two line bundle sums to make statements. So there are no tricks here to sort of cut down the size. And what this means is that even relatively small cases for Picard number 2 and 3 with sort of those typical number of states, they have not been explored so far. So I'm not really aware of a trick that would allow you to systematically scan those spaces. So what do we know about physical monad bundles, which is not a lot? We know that if all the entries are positive, there are no models with a good spectrum. And if we allow 0 entries, then on the bicubic, we know this one model here, which was found a number of years ago, and in fact in the same paper here. And there is another example, which in fact comes by continuation from an abelian model. And that's pretty much it. There's not too much known. And so we thought for that reason, it is actually a good environment to try out these RL methods. Okay, so what we want to do is explore this kind of environment using RL. So here's the matching. So the environment consists of these two line bundle sums B and C, which determine the monad sequence, again, restricted in some way. The action is sort of similar as before, but because we want to maintain the, we want to keep the vector bundles with vanishing first join class, we'll have to sort of add and subtract simultaneously in both B and C in the same row. And then the reward is again computed in terms of how much a given state deviates from having the correct standard model spectrum, and the terminal state is a state with such a spectrum. Now, this is, of course, there's a detailed breakdown of what exactly that means. And I don't perhaps want to go too much into that. So here's a list of the various conditions that enter the calculation of this value and the reward. So let me not go too much into the details of that. I should perhaps say that these are relatively basic criteria. Anything that has to do with checking cohomology is at this stage, at least with conventional methods, too slow to be carried out during training. So the idea here is that we implement those basic things, and more sophisticated things to do with cohomology we check later. Okay, so I said what the reward is. So let me tell you about the results. So first thing, we did this on the bicubic. So this is the same manifold as before for the line bundle case. And we started with constraining our entries to be semi-positive, like here, with the rungs being 6 and 2. So it's about 10 to the 11 states. And very nicely, the pattern of what you observe during training is very similar to what we've seen for the line bundle case, but now note that the environment is a lot larger than there. And so maybe the curve to concentrate on is this one here, which is again the fraction of terminal states during training. And this sort of explosively rises from close to 0 to close to 1 at some point during the course of the training. Again, meaning that basically 100% of states are being led to terminal states rather quickly. So the trained network, which I have to stress, has only sampled a very small fraction of all the states, about 10 to the minus 5 in this case. First of all, it finds one model, which is the known model in this case. So the model I showed you before and its permutations, but it doesn't find anything else. And that probably indicates that within this class, there isn't another model. It leads to this model and its permutations for almost all starting points. And it takes about 11 steps on average to get there. So that's a good start, but of course we would have liked to find new models. So we have sort of extended the search space a little bit to also allow for negative entries. So similar situation by cubic and so on, but now we allow slightly negative entries here. And the curves, the training curves, which I won't show again, they sort of look very similar as before. The fraction sampled is again very small, but it is again very successful. It ends up leading to terminal states with 100% probability at an average length of about 15 steps, and we now find other terminal states other than this semi-positive model from before. 59 initially, but then if we start imposing some of these constraints that we couldn't impose during training, it eventually boils down to 17 new models which look consistent and have the right spectrum. So the upshot here is that it is possible with this method to explore these relatively large environments, so 10 to the 12 in this case, and you can find states which are standard model-like. And then we've become a little bit more ambitious, and we've looked at a manifold with Picard number 3, which is given by this sort of triple trilinear with the same range of entries. And again, this is successful. It takes a bit longer than before, so this takes about a day on a single CPU. But again, it only samples a tiny fraction of the environment, and it's a very successful trained network. And we find a very significant number of terminal states, which reduces somewhat once we impose the more refined constraints. But we think that at the end of the day, there are probably about 500 among those which are consistent and have the correct spectrum. So this is in some sense a new database of standard-like models on this manifold here, which I think you would have a hard time finding by just conventional scanning methods, given that this covers an environment of 10 to the 19 states. And so here is something that you can extract from the trained network. So you can ask those various properties that we want to satisfy for these to be good models. Are they satisfied in any particular order as you go along episodes? So in other words, can the trained network teach us anything about the way that you want to build these models, about the order in which you want to impose the various constraints? And these curves indicate that the answer to this might be yes. So for example, this blue curve here corresponds to the to the value contribution of the index. So the more negative, the worse the index match. So the shape of this curve is telling you that the index is something that is verified relatively late in this process. And in fact, the thing that seems to be satisfied last is this purple curve here, which is the equivariance condition. So this might give you certain hints on how you might go about building these models if you do it yourself. Okay, so when I gave this talk at String Phenomenology, Sven asked about genetic algorithms, which was a nice question, and we thought it might be a good thing to see if genetic algorithms can also address the same problem. And so here is what we found. So let me just say a few things on genetic algorithms. I mean, the nice thing is that we can sort of take the same environment. So we take the monad environment given by these pairs of matrices B and C, or pairs of line bundle sums. And for the purpose of the genetic algorithm, we just convert these into binaries. And then we assign a fitness to each of these binaries, to each of these individuals in the genetic language, so to each monad. And for this fitness, we use the same value function that has been underlying the RL system. Then, as is standard in these methods, you create a population of these individuals, so a population of these binaries, 250 in our case. And the initial population is then evolved by crossing, which is a process that is controlled by the fitness of the individuals, and subsequent mutation. And the goal or the hope is that after doing this for a certain number of generations, you then end up with a population which has a lot of fit individuals. And in our case, that means terminal states, so standard models, in other words. So here are a few preliminary results of what we find. So this is the number of generations here on the x-axis, and on the y-axis is the number of terminal states within the population. And as you can see, this is actually quite successful. So after a relatively small number of generations, this goes up to about 40%. So 40% of our 250 individuals will be standard models after this time. And if you run this this sort of evolution for a number of times, 10 times in this case, each for 250 individuals and about 500 generations, you find about the same set as models as was found with RL. Oops, sorry. And so here's the same kind of plot for the other manifold, the trilinear manifold, and that turns out to be equally successful. And we find in 10 runs, we find about 750 models, which is somewhat less than with RL, but presumably in this case, you need more runs to get the full set. So if you ask which of these two methods is more efficient, then the answer is perhaps not totally straightforward. So here's a rough comparison between genetic and RL. So here's the number of visited states during training. This is the number of terminal states found. And for the bicubic, which is what this graph is for, you can see that the genetic actually looks like it's a bit more efficient. Whereas if you do the same thing for the other manifold, the trilinear manifold, it looks like that reinforcement learning is doing somewhat better. Okay, so that's the end. So I get to the conclusion. So I think I've convinced you that reinforcement learning can engineer topological properties, and it can learn the rules of building model geometries with prescribed properties. And in this way, we can explore large geometrical string environments, which would not be could not be explored with systematic scans. And we can use that to find, for example, models with a physically successful spectrum close to the standard model. And the trained networks that you obtain in this way can then literally be used for string model building. And I've also shown you that the genetic algorithms also look very promising in this context, and at least on this monad environment do perform quite well. So there's lots of questions, lots of extensions, other models, including more sophisticated model building constraints, different string constructions, including the moduli sector of the theory, et cetera, et cetera. The most important question that we have at this point is, how does this really scale with the Picard number? So far, we've only done this for relatively small Picard numbers. Does this really scale up? And is this possibly a way of exploring the entire environment of string vacuum? So with that, I finish, and thanks very much for listening.
Okay, thank you very much, Andre, for the very nice talk. Maybe we have time for some questions.
Tristan is raising his hand.
How do you see the raise?
No, I was actually clapping.
Oh, okay. All right, thanks.
So any question? I have one myself for curiosity. So at least in the models you studied, so you find, for instance, in some models you found like order 500 standard model like things.
Mm-hmm.
How does that compare to the to the total number of possibilities? Let's say finding the standard model is like 0.
Yeah. So within this class, I said there were about what did I say? About 10 to the 20 possibilities, right? So it's a tiny fraction of this total number, which corresponds to models with the right properties. So it's a sort of a needle in a haystack kind of problem.
I see. So it seems Sven Krippendorf has a question.
Yeah, thanks, Andre.
Hi.
Great to see the update from String Pheno. So I have a question in the sense of when you show these, compare these methods,
Mm-hmm.
do you also look at the quality or the properties of these terminal states? A sense of.
Well, I mean, they satisfy the properties that I've listed on one of the slides, and that is exactly the same between the two methods. So in that sense, it's a fair comparison.
But among the different ones that you see as terminal ones, are they always like drawn to the same ones, or how diverse is the population, so to say? That's the kind of.
I mean, so for the bicubic, we've looked at this. I mean, this is a bit preliminary, but for the bicubic, we've looked at this in detail, and the RL finds, I mean, with sort of minor differences, the same set of models as the genetic method. Okay. And I think I'm right, but Thomas might be able to confirm this. It is more or less the same for the other manifold.
What, for the trilinear? In terms of, are they similar? I haven't analyzed that one in detail. Which ones are similar?
Okay.
But it's,
and let me not say anything. So,
okay.
but at least for the bicubic, it seems to end up with roughly the same set of models.
Yeah, that's true.
Okay. Thanks. Thanks.
We can afford one more question. James, you had a question?
Yeah, Andre, great talk. Also, I enjoyed hearing the update from String Pheno. A simple question is, so you introduced this binary state representation rather than working with the monads in the way you did with RL. When you compare them, are you comparing RL on sort of that bit flip environment or the original RL environment?
I mean, it's sort of the same environment. I mean, it's literally the same piece of code, except that in one case, the integers are just converted to binaries.
I see. So it's literally the same action space, just encoded differently.
Yeah.
The bit flips on the binary actually do exactly what you would have done in the other description.
Yeah. I mean, it's literally just a different representation of the same thing.
Got it. Okay. Yeah, well, that makes my other question not relevant. So thanks.
Okay.